Okay, so let's get going. What I'd like to talk about today is firstly talking about the configuration of Python to use the Flownex API, what packages in Python you're going to require, any other prerequisites or any other need to knows before you can actually start using the API. Then I'd like to talk about the Flownex API documentation, where you can find it, what the most important sections are, basically what code should you be using and where can you find this code. Next, I'm going to look at a practical example where we add components using the Flownex API. So we basically use the network builder library to add components and construct a network automatically from a Python file. And then towards the end, we'll look at converting that network into a parametric study. Not only just changing inputs to components, but also changing whether or not components are inserted entirely. So giving you a lot more flexibility around the style of the parametric study. You get a lot more control than if you were just to use a parametric table in Flownex, for example. All right, so a bit of background. Systems with many components, typically the systems that I've seen where this is particularly applicable would be cooling channels and gas turbine blades. These components have hundreds of holes in them, channels, and ultimately specifying the inputs for all of these components by manually dragging, dropping components and adding them to the inputs pane can be very tedious and also very highly prone to user error. Remembering to offset each hole to a new radial location is something you could easily forget, and is not that easy to track if you solve your network. There's no clear way for you to recognize that you've forgotten to increment a particular hole's radial position. So what is a convenient thing to do is instead to represent these complex networks in a data file. This data file could be extracted from some CAD geometry, or it could simply just be an Excel file where you describe the main features and say a constant offset between components. You could then use a code like Python to read in this data file, interpret it, and then generate components automatically using loops to minimize the time that you spend coding, and then at the same time incrementing all the inputs correctly so that the inputs for the components are specified exactly as you intended. In terms of using the Flownex API, what we're trying to do is first have an environment where we can issue .NET commands. So this is available through most of your standard programming languages. C# and C++ can do this on their own. Python is able to do this with the Python Net plugin. There are some other versions of Python that will also be able to do this, but we found that the Python Net package plus your standard vanilla Python are the easiest way to get this working. That's basically all you need to start working with the Flownex API. We have created a flownex.py file. If you look in the help tab of your Flownex install, there is a Python button. This flownex.py file sits inside of that folder along with a simple example. Other packages that are particularly useful when it comes to this type of automated network building is the pandas package. This is available in Python. It's useful for database management and also analysis. It allows you to read in CSV files in one line of code. You can write to CSV very easily. You can read in an entire data set and then iterate through each row with minimal code. So personally, I find the pandas package very useful. And then on top of that, NumPy as well. If you ever looking to do any array processing or basically any operations where you're going to have arrays or matrices, NumPy is a very good library for that. NumPy is a prerequisite for pandas, so if you've got pandas installed, chances are NumPy is there too. Myself, I use Python in Windows, so I use Anaconda as my package manager. Inside of my Flownex Conda, these are the packages that I have installed. So the main ones are the pandas and PythonNet, along with your standard Python installs. Myself, I use Python 3, but you could potentially be using Python 2 as well. And then on top of this list here, one of the other packages that I tend to use very often is the regular expression module. Some people call it regex or regex. It's basically a string handling package. With the Flownex API, we're going to be sending values as strings and receiving values as strings. So it's useful to have some kind of package that can do some string handling, just help you formatting the strings better and extracting just numerical values or extracting text, for example, if you need to. All right, so if you're looking for the API documentation, you can go to the Flownex help button. You'll see the Python link is over there as well. That's where you'll find that flownex.py file. The API user manual is a button there. If you click that, it opens a new window with the entire Flownex API documentation. It has all the classes, and then inside of all those classes, all the properties, methods, and fields that you can access. Everything you need is inside of this file. It's a little bit cumbersome in the sense that it's described in a way that programmers are usually familiar, but if you look in the right places, you should be able to find your information very quickly. So to help you look in the right places, these are the three sections that I would consider most important. There's the network builder interface. This is the area where you can add and remove components, maybe even add drawing pages or delete drawing pages. The next one is the property interface. This is where you're going to be able to set inputs and get results from components. And then lastly, the simulation control helper class. That's going to give us the ability to solve our network in both steady state or transient. Okay, so let's get into this. What I'd like to do today for building a network is to use an open Brayton cycle as an example. So to do this, we're going to build the network procedurally, and the steps that I tend to follow are here on the slide. First, we deal with the imports. These are just any of your Python modules or Python packages that you're going to need for the code. Then we're going to write some basic code to open Flownex and create a drawing page. We're going to add components to that drawing page, link the components, and then specify inputs. Just as a small nuance, we're always looking to link components before specifying inputs. I'm not sure if you've noticed this, but if you, as you link components in Flownex, the input options on those components change. So it's just important to link before specifying inputs. Next, we're going to solve the network, save it, and then extract some results. So let's jump across to the code, and we can start looking at some of that information. Just as a small aside, all of the code that I use today, or in fact all of the files, we'll make available to download. So in the next day or two, you should be able to download all of these files. So don't worry too much about the detail of every single line of code. This webinar will be recorded, so you can look at it at a later time, but also the code will be made available so you can work through it line by line if you're looking to implement any of this for your work. First, we have this flownex.py file. As I mentioned, this is included with Flownex. This is just a couple of predefined functions to help make your life easier when it comes to standard routines like launching Flownex or opening a project. It takes a bunch of the overhead out and just allows you to call these simple functions. You'll find common things like starting simulations, stopping transients, getting outputs, etc. All right, so down to the real code. In terms of our inputs, we import the Python net, that is just represented here as CLR. We import that flownex.py file. We then import RE for the string handling, and then a couple of other packages which I use for copying files, deleting files, etc. It's just a few others. In terms of the overall setup, what I have is just a variable at the top for my page name. This is going to be the page that I build the actual model on, then a file name for the Flownex project, and then inside of Flownex, or through the API, we have different options for whether or not you would like to use the current instance of Flownex and then issue API commands to it, or if you would like to create a new instance of Flownex every single time you run your code. So in this case over here, what we're doing is we're going to use the current instance. So Flownex will be running already when we start our code, and then the API will just issue commands directly to that instance of Flownex. Just as a small bit of information, to configure Flownex to work with the API without opening a new instance, you have to go to the Settings tab, click on Project, open Application, and then just enable this setting under API COM. This setting says use only one instance for all API clients. If that is selected, you can then use the API to communicate directly with Flownex without opening a new instance. It just makes testing your code a lot easier, and also it means you don't have to wait for Flownex to load every single time you run your code. You can just use the existing instance that's open. All right, so just before we go any further, we have a couple of functions over here. These are just predefined functions to help with reducing the complexity and increasing the readability of our code. So we're issuing some commands to the API to add components to the drawing page, specifying the name of that component and the positions of the component. But what I'm doing over here in this function is ultimately trying to simplify the inputs. If you look at this add component to page function, you can find this in the API. By the way, let me just show you how we get there. So under the network builder interface, we can find network builder methods and then add component to page. And you can see all the arguments for this particular function and all the syntax that you need to worry about. All right, let's go back to Python. So what I'm doing over here is creating a Python function that is going to call this API function, and we're going to reduce some of the inputs. So the page name can be declared as a variable above here, so we don't need to specify the page name as an argument to our function, so we can get rid of that. If we're going to be creating a function called add node, then it's only going to ever have to add a node. So in terms of the identifier for that component, we can hard code that as a node. To get this particular identifier, all we need to do in Flownex is right-click on the component and click Copy Type Name. If we then paste that, you'll see we get flownex.components.node, and that's the input that we use here for the component name or components identifier. Next, we add other information like the name of the component, what we'd like it to appear in the GUI as. We put in the X position, the Y position, and then these last 4 entries on the end here, I typically hard code these. The first 2 are the X and Y sizes. So for a node that's 15 by 15, you'll notice the nodes are quite small compared to the other components. Just out of interest sake, the grid that you see here in Flownex is 25 by 25 each block. So a node over here is just smaller than 1 block. The standard components over here are 50 by 50, 2 blocks by 2 blocks, and then boundary conditions are a little bit bigger. They're 30 by 30. You have the ability to obviously size these however you like, but I tend to stick to the standard sizes. If you're interested about the coordinate locations, so each component has a size attached to it, but also X and Y coordinates. If you're curious as to where the coordinates are defined from, our origin is here in the top left corner. The positive Y direction is down, and the positive X direction is to the right. So this component over here has a Y value of 100. If I were to move it down, its Y value would update to 175, for example. Okay, just to show you exactly where this information is, this is once you've clicked on the component, you just select the View tab. You would normally have the Input Properties tab. The View tab has all of this information. Okay, so yeah, as I mentioned, what we're doing over here is adding or creating these functions that can deal with your standard inputs. We're trying to just clean up some of these API calls so that in our main code, we're not seeing long lines like this, we're seeing more simple lines. Inside Python, and one of the reasons why I really like the language, is you're able to define functions with pre-allocated variables. So here we can have add node with view equal to false by default and view name equal to view1. This means that we can call the add node function and only give it 3 arguments. But if we wanted to add additional arguments, we can just override those old inputs. So we can have a name, we can have an X position, we can have a Y position, and then we can add additional information. Like if we would like our node to be added as a view, we can instead set view equals true. This will overwrite that variable inside here, and then the logic in these if statements will, instead of calling the add components to page method, it'll call the add component view to page method. We can specify the name of our view by just overwriting the view name variable as well. So setting up these functions in advance just gives you or makes your life a lot easier down the line when it comes to calling and adding all these components. It'll save you a lot of time in the long run. Another function that I like to predefine is the link components. So here we're connecting two components together. So the most common way that we connect components is these fibers and the data transfer links. So for the fibers themselves, the most important thing to note is that the order that you specify the connection in is important. This component has two fibers connected to it. So if we specify the name of the node followed by the name of the resistance, we will have the upstream fiber connected. If we specified the name of the resistance and then the name of the next node, we would have the downstream fiber connected. You basically specify the names in the order that the fiber is pointing. So the name 1 and name 2 inputs are important. The position is important for the connection itself. Here we've gone and overloaded this thing as well. So we've defined a lot of predefined Boolean variables for whether or not you would like the components to be linked just as normal components, or if they are views of other components and they need to be linked. There is a case when there is a component with more than two fibers. This logic that I spoke about with specifying the node and then the component works if there are two fibers, but if there are three fibers, for example, then that logic falls apart. So that common case would be, say, the heat exchangers. Here we have one upstream fiber, but two downstream fibers. So specifying the order isn't enough to explicitly define which fiber you're using. So in that case, we specify the fiber name as well. So if you follow the logic through the if statements here, you'll see that we add the fiber name as an argument when we call the link components method from the API. Beyond that, what we're looking to do is also add a link components option for data transfer. Here I'm using a Boolean again. And then for data transfer, all we need to do is specify the name for the component that the data is leaving, and then the name for the component that the data is going to. And with that, we should be able to fully define our data transfer. Okay, so let's get into the particular problem. As I mentioned, I would like to demonstrate this with an open cycle Brayton network. So we have an inlet from atmosphere, we have a pre-cooler, a compressor, which I'm modeling using the basic centrifugal pump. We then have a intercooler, another compressor, a recuperator. This I'm modeling with a flow resistance here on the primary side and a flow resistance on the secondary side with the composite heat transfer connecting them. We then have another flow resistance representing heat input to the system, a HP turbine, a reheat section, an LP turbine, and then the secondary side of the recuperator before exiting to atmosphere. So I don't want to focus too much on the flow modeling. I want to look more at the communication using the API. I have added one custom component. So if we scroll to the top, you'll see I've created a custom compound component called efficiency script. This here is just a single script, and I'm using it to calculate the efficiency of the cycle. What I'd like to do to demonstrate the functionality is to add and remove different features. So add a pre-cooler, and then remove the pre-cooler and see what change that has on the efficiency of the cycle. So to ensure that I can have the efficiency calculated, I've just created this script that allows me to get an efficiency result, and I can extract that later using the API. Okay, just a small bit of information. If you are going to be using compound components like this, it's just necessary to create the compound components, save them in a project, and then use that project as a template for building from the API. So when we run this code, I'm going to delete this drawing page, and then this Flownex project will not have any drawing pages, but all of the configurations for the compound components, if you wanted to configure the solver settings or anything like that, could all be done ahead of time. And then Python can start with this sort of pre-configured project and only have to worry about adding components. Okay, so when it comes to actually specifying the code, we have a couple of imports. These are imports related to the actual .NET commands. We then need to specify some small routine things like the folder location where the files are. I have a directory created for the current location, so a template basically. This is the empty file that I can use as a template for my project. So I'll have that location, and then I'm going to copy that to a new folder and then use the project there. We have some code around whether or not we're going to be using a current instance of Flownex or whether we're going to be using a current instance or whether we're going to be launching Flownex through the API. In this case, if we're using a current instance, we don't have to worry about creating a copy of the template files, and we don't have to delete the old template files. So all of this code can be skipped if we're going to be using a current instance. The next thing we want to do is launch Flownex. One thing over here just that I'd like to point out is please check this version number. Whenever you use a new release of Flownex, the version number obviously changes. So if you're using the API to communicate with it, please make sure that your version number matches. This is something I forget from time to time. Once again, we have different conditions whether or not we're using the current instance. Here, we're either looking to open a new project where we specify the project directory, or we're just looking to use an existing instance. Okay, then the next step is we're going to be adding a drawing page. So here we use the command or the method add page, and then we specify an argument as the page name. If you remember from earlier, I specified that at the top. So here we have the page name, then we create an object for the current page and then change the size of that page. So here I've just set the size to 1000 by 500. You can set that size in any way you'd like. I've just made it small so that it's nice and presentable, but you can always use some functions to potentially calculate the amount of space you're going to need on your drawing page to add all the components that you're looking to add, or alternatively, you could always just oversize your drawing page, whatever suits you. Okay, then we can add a background image. So with this line of code, we're using the method set background image. We give the page name and then the location of the image. Inside the folders, I have a simple PNG file with some simple graphics to illustrate the main components in the cycle, and we're just adding this as a background image. So if you look in Flownex, you can see the background image behind all those components. Okay. All right, that's about it for the pre-processing. The next step is then listing the components or the cycle inputs and then adding all your components. So for the cycle inputs, I'm listing them all here in advance because what I'd like to do in the next step is to modify these cycle inputs by reading them in from a data file, successively changing the inputs for each row in that data file to simulate different cases in a parametric study. So I'm grouping them all in the same place just so that I can easily change them later on. The type of changes that I'm able to make would be ambient conditions like pressure and temperature, the exit temperature of the pre-cooler and the exit temperature of the intercooler, the intermediate pressure for the compressor, the efficiency of the compressor, the mass flow rate through the system, the overall heat transfer coefficient and area for the recuperator, the combustion inputs in the form of the temperature of combustion, that would be your high pressure turbine inlet temperature, and then your reheat temperature, and then some inputs related to the turbines, like the pressure ratio for the high pressure and low pressure stages, and the efficiency of that turbine. So all of these inputs sit in one area. Later, we're going to replace these with like reads directly from a data file. Okay, the next step, we're going to start adding components, but before we add the components, I like to create a naming convention for all my components. This is completely up to you. I've hard-coded all of them, but if you are going to be doing this from a data file, you could theoretically name the components procedurally. So every row in the data file could have a particular name attached to it, and you could just read that name in for the components, or add a prefix, or add a counting variable, anything you like to create these names. The only thing to keep in mind is that this name must be unique across the entire Flownex project. So however you decide on your naming conventions, just ensure that no two components can have the same name. Okay, what follows from there is then adding the components. So here we're using that add node function that we defined at the top. You can see it cleans up the code considerably. We have add node instead of the alternative, which would be this over here. So we have that versus this. So personally, I prefer this, but it's up to you in how you would like to structure your code. Okay, so here we're specifying the name of the components, the X and Y coordinates. From earlier, if you remember, we can select a component, click the View tab, and see the X and Y location. Here I'm hard coding them. In some kind of scenario where you're reading in a lot of geometry from a data file, I'd recommend you put in calculations for the X and Y coordinates. So set a variable for the X stepping and the Y stepping, for example, and then inside of the for loops that read each row or each column, to automatically increment the X and Y positions based on a counting variable and then a predefined step. If you'd like more information on how I've done this in the past, please feel free to send us an email. I'll give you some examples there. The next thing is just adding nodes, then some boundary conditions, then adding the flow resistance components, the composite heat transfer, the basic centrifugal pump, turbines, and then the efficiency script. So all of this, as I showed earlier, was all defined above. There's nothing particularly fancy about it. The next step is then to link the components. We're using that link components function that we defined earlier. So here we only have to specify 2 arguments. But if you remember, we do have the ability to specify additional arguments. So if we wanted to specify that these were data transfer links, we could just say data equals true. I'll show you this in a bit. Anyways, okay, so we link our components. This is linking boundary conditions to nodes, then linking the components node to resistance. Remember that when we link these components, we must always keep in mind the direction of the fiber. So here we're linking node 1 to flow resistance 1. So node 1 to flow resistance 1. The direction would then mean that flow resistance 1's upstream fiber is connected to that node. It's a small point, but it's important for you to grasp the concept. Otherwise, linking components becomes a nightmare. All right, this continues for all the components in the rest of the network. I don't want to spend too much time on that. Then we get onto the data transfer links. So here we're using the same function, link components, but then we're overwriting the value for data, setting it as true, and specifying the data names. So the actual values we would like to transfer. We specify the name of the components that the data transfer links connect to, but then also the name of the variables that must be transferred. So to find those variables, we can either right-click on a data transfer link and then look at the values we see here. So the from property is D power, and the to property is inputs compressor 1. Inputs compressor 1 power. We can get that information and add that directly to our actual function call here. Or alternatively, if you just want to copy this, the way in which I do it is to click on the component, go to the results section or the input section, depending on whether it's the to or the from data transfer. Right-click on the variable that you would like, and then for the component that the data is going from, you copy the internal identifier. So in this case, you should see that should be D power. And then for the component where the data is going to, you copy the internal identifier. The display identifier, not the internal identifier. And here you'll see that. So these names over here match the values that you need to input into your links for data transfer. Don't ask me why this is the internal one. This has just been a mystery for me, but it seems to be consistent across all the components. So you shouldn't have any problems with your data transfer links, as long as you remember the upstream side is the solver variable, basically the internal identifier, and then the downstream side is the display identifier. For all of your other cases where you need to reference a property, you'll always be using the display identifier. So the only special case where you need an internal identifier is for the upstream side of a data transfer link. Okay, so if we've now specified our data transfer, we can go ahead and start specifying inputs to our components. So here we specify the fluid. First we get a component, so here is the node 1's name. We use the .getComponents method, and then this creates an object called N1. with that object, we then get a property from its display name. The value that we're going to use over here, this fluid data reference, we can get the input for that by just clicking on a node, going to the input, which is in this case the fluid data reference, right-clicking, copying the display identifier, and then pasting that inside of our code. And you'll see that the value that you see here, let's do that. The value that you see here is exactly the same as what I have inserted inside of that function. Once we have the property, we can then set the value. In this case, we want to set the value to an air fluid, but the actual input for that is over here. So I usually just copy that and then paste it in my code. So this is the name of the fluid. That's the name of the folder. This is the class of fluids, whether it's pure fluids or two-phase fluids. And this is which database it's in, whether it's the master database or project database. Okay, next we can go ahead and specify other inputs like boundary conditions. So here we're going to specify that the upstream boundary condition must be a total pressure. So to do that, we click on the boundary condition, get the boundary condition options display identifier. If you look at that, it's boundary conditions pressure boundary condition, which matches what we have over here. We then set the value from string, and we set that equal to the fixed on user total value. And you'll see that's fixed on user total value there as well. All right, when it comes to setting values though, up until now we've only had to set string inputs. If you want to set a value, you need to first convert that value into a string. In Python, you just use str. And then Flownex will always interpret that string in base SI units unless you specify a unit attached to it. So personally, I like to add units just because it makes the inputs a bit more intuitive. So in this case, I'm adding kilopascals. One thing to note is that there is a space between the number and the unit, and the capitalization of the unit is also important. So kilopascals, for example, is a lowercase k, a capital P, and a lowercase a. So here we just append the two strings, or concatenate the two strings rather, and this value is then sent as the input for this pressure value. You see boundary conditions pressure over there, which we would obtain by just copying the display identifier. Okay, we basically repeat this process the whole way through. We can do the same thing for temperature. Degrees Celsius is very easy to do as well. Just a small tip, if you hold down Alt on your keyboard and on the numpad type 248, it's the character code for the degree symbol. So you can add degrees Celsius or degrees Fahrenheit very easily that way. If we keep going down, we have all of our inputs for the remainder of our components. And then right at the bottom, once we've specified all the inputs for our components, we need to solve our project and save it. To solve the project, we first need to create what's called a simulation controller. This is basically a component that will basically manage the solution. So we create the simulation controller, sending it the Flownex project. We then solve steady state, sending it the simulation controller as an argument, and then sending it also a timeout. As with most external code communicating to another code, we have the software is going to have to wait for results. So in my opinion, it's always good practice to have a timeout there. You can modify this code to not have a timeout. If you go through the API documentation, you'll see that there is another solve steady state method that doesn't have a timeout. Next, once we've got our solution, we disconnect our simulation controller, giving access to the user again, and then we can save our project. Once that's all done, we can go ahead and export our results. So here, in exactly the same way that we specified the inputs to a component, we can extract the results. With the inputs, we use the .setValue from string. With outputs, we just use .getValue as string. You'll notice getValue string has no arguments, but instead returns a value. So we just assign that to a variable. A small bit of information, when Flownex returns the result, it's going to return a string that looks a little bit like this. It'll have the efficiency value, which is maybe 0.2991 and some decimals. Then it's followed by the word efficiency and then the unit. So if we go back to Flownex, you'll see it's the value followed by the name of the result followed by the unit that it's in. So when we extract, this is the contents of that string. This is not ideal for our uses at the moment, so what we need to do is a bit of string handling. So here I'm using that regular expressions package. We're looking for any digit followed by a decimal followed by digits, and then we extract all of that, convert this from a list into a string, and then convert that string into a float, into basically a decimal number inside of Python. And we multiply that by 100 and print it to the console. So this line over here might be a bit intimidating to users that aren't very familiar with Python, but it's pretty standard in terms of string handling. Okay, so let's go ahead and test the code. So what I have over here is just the completed version, so I'm going to delete that. I'm going to keep this project open though, because I'm going to be using the API with the current instance set to true. So we're going to be using a current instance instead of opening Flownex. So if I run my code now and then switch across to Flownex, you should see it add a drawing page. It will then add a background image, add the components, link those components, specify the inputs, solve the network, save the network, and export the results. So I don't know if you saw, but it basically added all the components and has solved the network. If you look at each of the components, you'll see all of the results are populated. And then this efficiency result on the script has now been read by this Python code and has been printed in the console over here. So we can see 29.91 as our value. Okay, so this basically forms the basis of our parametric study. The next step now is to specify some kind of cases for this parametric study and modify our code to allow it to change our network. So when it comes to a parametric study, my first step is usually to write code for the most complex case. That's exactly what we've just done. This over here is the case with all of the components inserted. All of our other cases will involve removing some of these components and seeing what effect that has on the overall efficiency of the cycle. In your particular example, it might require replacing a component with another component, but try and think of the most complex case and code that up completely, just to make sure that you're comfortable with all of the inputs, with the layout of all the components in terms of its X and Y locations, and then from there move on to automating each of the cases. I would recommend just starting with a single case as a sanity check, basically. Okay, the next step is then to create some kind of input file data structure. So the way in which I did that was to create a CSV file. If you remember from the Python code, we had a couple of values at the top of the file where we stored the inputs we were going to use for our cycle. So let me go back to that code. We see it over here. So here we're specifying ambient conditions, compressor inputs, recuperator inputs, etc. So these inputs here, I'm going to now represent in a data file instead, so that Python can read it in and then transfer it to Flownex. So as a user, you would be modifying this file instead of modifying the code itself. The code is written generically and the data file changes. So in this case, each row is going to represent a different case. And then whenever we don't want to have a component in our network, say we would like to remove the precooler, we simply replace the entry for that value with negative 999. Negative 999 has no significant meaning. It's just a completely invalid input. There is no case where negative 999 would be a valid input for temperature, pressure, heat transfer, area, etc. So it's very safe to use as a null value. So if we ever see this value, we can write logic into our code to not add that component. Here I've then just gone and added additional cases, successively removing more and more components. You'll see each row has more of these negative 999s, basically removing more and more of the components as we go. All right, so to actually import that CSV file, we're going to use the pandas package. So we need another import for pandas. Once that's done, our inputs are complete. Everything else inside the project remains exactly the same up until there. We create the drawing page the same way. We create the Flownex SE project the same way. It only changes when we get to our data inputs. So here I'm creating what's called a pandas data frame by using the PD, which is just shorthand for pandas, dot read CSV. So this read CSV function takes the name of the CSV file, the separator and the encoding of that file, and then we'll read this in and convert it to a data frame object. Let me close this. Okay, once we've read in our CSV file, we can look at iterating through each of the rows in that CSV file. So if you write the code over here, I will be our index variable, so that will correspond to the row number, and then row will be an object for each row, which will have entries for each of the columns. So row with the 0, so this format, will be the first entry in that row. So by writing the code like this, we can basically iterate through each of the rows, and then in each row extract information. So the code that you see over here is a bit long, but what it's basically doing is looking up the column index. I haven't hard coded this as 0. Instead, I've given the name of that column and asked this, or basically used the pandas commands to find that index on its own. I recommend doing this over hard coding it because we often add additional inputs to these data files, and then myself personally, I forget to sometimes update the indices that I've hard coded. So using these references that link to the name and instead of to the column number are much safer. Okay, so we basically do this for all of our variables. Here I've just named the columns to be the same as the variables. You don't obviously have to do that, but it's just easier to match them. Then I've included some logic over here. If, for example, the pre-cooler exit temperature is -999, then this variable that I'm calling pre-cooling will be false. So I'm creating a couple of Boolean variables early on that will determine all of the possible permutations of my network. So whether I would like a pre-cooler or not can just be determined early on. I do the comparison to the data file, and then thereafter I can just use a Boolean variable. What that basically means is that your code that follows for adding components can read more like if recuperating add that node. So if we look at our network, if there was no recuperator, some of the nodes in the network wouldn't be necessary. So we can skip placing those components. So by using this logic of using these Boolean variables that have nice names, it just makes the code more readable. For our naming conventions, as I mentioned, each name has to be unique across the entire project. So I've put in a prefix with the word case and then the number of that row. So by doing that, I can keep my old naming conventions for all my components, but I've just put on case 0, case 1, case 2, case 3 as a prefix, and that will make sure that all my components across all the drawing pages still all have a unique name. Okay, that about covers it from the logic. What follows from here is just a lot of if statements on whether or not we should add components, then a lot more if statements on whether or not we should link components and where those components should be linked. And then lastly, what components need inputs and what those inputs should be based on these permutations once again. So I don't want to go into too much detail here. This gets very technical and requires a lot of logical thinking without adding much value. So if this is very interesting to you, I encourage you to go through the code afterwards or look at the recording of the webinar and just pause and look at these moments. Okay. Once we get to the end, we can then solve our network exactly the same as before, and then we can export the results. You'll notice I'm using another for loop down here, and this is not inside the for loop. What I'm doing is creating a new drawing page for every single case, and then solving after I've created all the drawing pages. It wouldn't make sense to create a drawing page, save, create a drawing page, save. Instead, what I'm doing is just creating all of them and then solving once. You can obviously do it in whatever fashion you like, but I see this as a more efficient style. As a result, I then need to write the same for loop structure down below and then use this to extract the results from each of the efficiency scripts on each of those drawing pages. Those values are extracted in exactly the same way using the string handling and then printing to the console But then one more change is that we're adding a value for efficiency to our pandas data frame. The data frame is called cases in this case, and the value is being set equal to this efficiency value that's just been calculated. Once that's all done, we take our cases data frame and we write that to CSV and overwrite our old CSV file. So ultimately what's going to happen is we're going to append a new column to our CSV file called efficiency, and the value in each row will be the efficiency for that particular configuration. Okay, so that about covers the code. So let's go ahead and delete this again, and then let's run the parametric study code. So here, when it's building each of the cases, the API is calling all of the, or Python is calling all of the API commands, and the user interface doesn't keep up at this point. All of the components are still being added correctly, don't worry. It's usually by the time that it solves and the processor is freed up to the user interface that we then are able to see all the visualization again. So here you can see each of the cases where the components are added or not added based on what we had inside of that data file. So if you remember the first case having all of the components, and then successive cases basically removing components as those features are removed. If we now go back to our CSV file and open it, we can see that there's now an efficiency column, and then the efficiency of each of those cases has been saved and stored in that row. You can obviously save a new CSV file or put the data somewhere else, but this is just one way in which I tend to use it. Okay, let's go back here. So just to sum this all up, from my point of view, when it comes to these very large networks or networks where you can very logically describe where the components should be added or shouldn't be added, and you're looking for that extra flexibility in your simulations, trying to streamline your workload, using the API is an ideal way to do this. This is something, as I say, is very useful for very large networks with lots of components, but can also be used in other examples and other scenarios where you perhaps read in geometry from a CAD file and automatically construct a Flownex network. The data file that is generated after reading in the CAD can then be directly used as an input in a case like this and automatically construct a Flownex network. So if you're looking to reduce the sort of tedious and error-prone simulation tasks, this is a good place to look for a solution. When it comes to getting comfortable and confident with all of this coding, the best way in which I learn is to learn from the examples. So as I mentioned, all of this code will be made available. It should be ready in about a day or two, and then you'll be able to download it and go through it at your convenience. And then lastly, if you ever get stuck in any of this coding, please feel free to contact us. Reach out to your closest Flownex reseller. They should be able to help you through most of it, and if they aren't available or if you're looking for more assistance, please feel free to contact us as well. I'd be more than happy to assist you with structuring your code better, or with assisting you in understanding some of the higher level coding functions that are required.